Okay, so uniform acceleration with drag. That means that mass times acceleration equals negative sum with, I'll say, linear drag, meaning that the drag force is proportional to velocity. Okay, so this is gamma V, and that's really it. This is net force, this is net force. Actually, gamma V plus some constant. I'm just trying to figure out what letter to use. I'll use F applied, an applied force. Okay? So it's like you're trying to push something through water, say a bowling ball. Now, if you got a bowling ball in your hand, don't get into deep water unless you know you can release it and not have it hook on to you, right? So in shallow water, you're trying to push a bowling ball through the water, okay? And you're just giving it a shove, so you're not trying to move your body through the water also. I mean, you can do that, then you have a different drag coefficient, but it's hard to walk fast in water. You can push the thing kind of fast, right? Okay? So you can just think of that as an example. Okay, well, acceleration is the second derivative of position function. Velocity is the first derivative. Okay? Now what kind of equation is that?
Second order.
Well, it's second order because you got two derivatives, right? And it's linear because you have an x double prime and an x prime, right? Now this part doesn't fit. You know, something times x double prime plus something times x prime plus something times x. So that's a non-homogeneous part. So we can write this as a non-homogeneous equation, mx double prime plus gamma x prime equals F applied. Okay? And at this stage, a couple of things we could do. We could divide through by m, and that's what we would usually do. But I'm not going to divide through by m, just to show it works no matter how. And that it's simpler if you do divide through by m. So I'm not going to divide through by m, partly to show why you probably want to divide through by m, but it's easy either way. It comes out the same. Okay? So, you gotta separate the homogeneous equation. Because we start any non-homogeneous equation by solving the homogeneous equation, if it's a second order or higher order with constant coefficients. Okay? And there's another thing we could have done to simplify it. It's actually a first order equation. It's a first order equation in x prime, because this is just the first derivative of x prime, right? So I'm going to show you a couple of things that we can do, but I'm going to solve it the way it's written, and then show you how it could be simplified. And what you want to take away from this is not necessarily the specifics of how to do this, but the idea that there are things we can do to simplify equations. We'll come back to these and study them in more detail. Right now, I want to get to some applications and show you how we can write equations for applications and equations that we can pretty easily solve using techniques that we've seen already in the first 2 weeks. Okay? Okay, so anyhow, and it's RT. Use lambda if we're trying to do eigenvalues, okay? And then this is really an eigenvalue too, but we will typically use R, because that's a notation the book uses, and it's a pretty standard notation. See, you got your books, incidentally. Okay, so our characteristic equation is mr squared plus gamma r equals 0, right? So we conclude that, well, as long as r is non-zero, well, let's go ahead and solve this by factoring. It's a technique you want to have. So it's r times mr plus gamma equals 0. Now my r's and my gammas might be a little difficult to distinguish if I write carelessly, so in the first place I'll try to be careful and then maybe not put so much of a gap in my r there. Yeah. And put a little curly q in the gamma. It won't be there in the r. So that's how you can distinguish it if I do get careless. If I get so careless I don't do that, though, I don't know what you're going to do. Probably fail the course because I can't write. We try not to let that happen. Okay, so what are our solutions? Now this is basic algebra 2. Okay? So this should be something that you understand, but you might have to stop and think about it a little bit depending on how much algebra 2 you used in your calculus course. Your solutions are r equals 0 and r equals negative gamma over m. Okay? Because if r is 0, well, that makes the whole thing 0. And if you've got negative gamma over m, well, you could write out the equation mr plus gamma equals 0 because the 0 property, multiplication. Okay? The only way the product can be 0 is if one of the factors is 0. Okay? And you set that equal to 0 and solve it, you're going to get this. But you can kind of do that in your head. If you can't, write it out. Yeah. Okay? And after you've written something like this out 100 times, just start doing it in your head. Just avoid having to write the stupid thing out. Okay? And then you're going to check back here. You multiply this by m, you're going to get negative gamma plus gamma equals 0. You don't just write down what you think. You write down what you think, and you check it out. You can do all that in your head, but if you're not comfortable doing it in your head right now, write it all out. Okay? And always check at every step, because when you get to my age, you're going to need to do that because you're going to write stupid things without knowing it. Okay? You always got to check yourself. Now you're at the stage where you haven't really totally developed your mathematical repertoire. Okay, and I've developed, a long time ago, whatever mathematical repertoire I have. Okay? So you through inexperience, me through, senility, or whatever's going on here, have to check. And you get feedback by checking, and I just say that because I notice that students are not in the habit of checking, so I don't know what our curriculum is doing to people, except putting calculators in their hands when they shouldn't, and dumbing it down so everybody can be above average. Okay, so anyhow, here we have all this. And made my hour look more like a gamma. I was trying to fix it. Okay, so our solution set to the homogeneous equation is going to be e to the 0t, e to the negative gamma over m t. I promised to loop in my gamma. Okay? And that's not a parenthesis, it's a brace. Okay? Which is just 1 e to the negative gamma over m t. Okay? So that's our homogeneous solution. Okay?
Why is it just 1? I know.
Because 0t is 1.
Oh, yeah.
It's okay, you gotta ask.
Yeah.
I understand.
Yeah.
I sometimes look at something obvious and don't see it right away. Although with long experience, I know to be careful about that, so I probably recognize it a little more quickly, but still, I get caught. Okay, so don't worry about it. Okay, so that's your solution set to the homogeneous equation. Then the non-homogeneous equation, how are you going to get F applied out of this? Well, how are you going to, F applied is constant, okay? Now, if F applied is something besides a constant, well, you have to try a different trial solution and hopefully be able to find it. Now, there's also the variation of parameters technique that will develop much later. Not that much later, you know, probably around November, okay? Late October, November. But the non-homogeneous equation, okay? Multiples of x prime and x double prime must add up to a constant. Now, what kind of functions can you take derivatives of and get constants? Sorry? I'm sorry?
Exponential?
No, an exponential function gives you an exponential function and it's not constant. Sines and cosines don't give you constants. Right now, let's just think in terms of power functions, sines and cosines, and exponential functions, which are the ones that usually apply here. We might expand the vocabulary a little bit. Your book even has a list. But if you understand it, you don't even need the list. Okay? So, well, first of all, you can't have an exponential or a trig function and end up with a constant. Okay? Actually, you kind of can, but the constant would usually be 0 for a trig function, and for an exponential function, what you would get turns out to be this. Okay? So those are kind of out. Just by trial and error, you start to learn that. It doesn't hurt to put an exponential function in as your trial solution. You'll find out that that's what you get though. Okay? So what else?
Power.
Okay, well, what power functions? Most power functions are out. Okay, like x to the 5th. Well, the second derivative is still going to be a multiple of x cubed, and the first derivative is still going to be a multiple of x to the 4th. You don't want those. Okay? You can use them. You'll find out that the coefficients have to be 0. Okay? You'll end up with a set of simultaneous equations, and if you do the matrix and reduce it, you're going to end up with lots of rows of zeros. For a linear algebra student, former linear algebra student, you might remember how that works. Or you're just going to end up with a bunch of simultaneous equations and a bunch of zeros. Okay? So, what derivatives of x double prime and x prime can equal constants? I mean, what functions have second and first derivatives, second and or first derivatives that end up constant? Well, what kind of function has a first derivative that ends up constant?
Natural law.
Okay, just what's the derivative of t to the 4th plus t cubed plus t squared plus t plus 5?
4t cubed plus 3t cubed plus 2.
Okay, so doing that, do any of these functions have Derivatives that are constant. T. Any multiple of t has a constant derivative, right? Okay? So, let's see, let's use a symbol I haven't used. Don't want to use A. I'll use capital DT. Right? Now, what's something that would give you a second derivative that's constant?
T squared.
Yeah, so multiple of t squared. We'll just say capital C t squared equals 2c t. Well, 2c when you take two derivatives, right? You get 2ct for the first derivative and then just 2c for the second derivative, right? And any other power is not going to give you a constant. Okay? So if your second derivative and first derivative, multiples of second derivative and first derivative are constant, you can't use anything higher, anything other than a t or the t squared. Any other power is going to give you something that isn't constant. Okay? Now the first derivative of this isn't constant, but that's okay because the second derivative is. Okay, well then we say and then we can actually put plus d in here. We could have any constant because its first and second derivatives are both 0, right? Okay? So we plug that in. Okay? Now when we plug that in, it's very straightforward. We just plug it into mx double prime plus and put x equals here so we know we're plugging in. So we get x double prime, well, x prime equals b plus 2ct, x double prime equals 2c. Okay? So our equation becomes m times 2c plus gamma times b plus 2c equals F applied. Okay? And then using exactly the same reasoning we use with partial fractions, which I hope you're reviewing, we get and yeah, make sure I'm just checking to make sure I'm not doing something stupid. Probably still am. But we get 2mc. That almost looks like m raised to the c. It's hard to write down here, sorry. But I can't read that there. It looks bad. It looks even worse with the smudge, but at least it's mathematically correct. Okay? So we get 2mc plus gamma b plus 2 gamma c and it's, I'm sorry, there's a C, there's a T on this one. I knew there's something wrong. I'm getting too many terms. Okay? Okay, well, it follows that this has to be true for all values of t. Okay? So whatever t is, this has to be a constant. Well, if t changes, this changes. So this coefficient has to be 0. If it wasn't 0, then different values of t would give you different numbers. It wouldn't be constant, okay? So left-hand side is not constant if 2 gamma C is not equal to 0, so C has to equal 0. And then two MC plus 2 gamma C, which I can write in factored form, has to equal F applied, and that's wrong. Looking at it as it was before and not looking at all of it, so let's do it right. Okay? 2MC plus gamma B. Equals F applied, right? But C is 0. If C is anything but 0, this doesn't work. So B is your applied force over gamma. Now this thing that I wrote down here is in the way. It's not important. Just up there to jog your memory. Knew it was going to be in the way. Okay, so now here's our x function. I'm just going to abbreviate applied. Okay? Where D is an arbitrary constant. Because D didn't appear down here, it could be anything. Okay. Now I'm going to call this x sub p. Used this term before, particular solution. It's a solution to the non-homogeneous equation. Okay, so our procedure is very straightforward. You just have to practice it a little bit and imitate the steps that I've done here. Of course, you have to adapt for the nature of the function you have on the right-hand side. But the procedure is simple. You solve the homogeneous equation, that's easy. If it's a second-order equation, the quadratic formula always gives you a solution. Sometimes it's a repeated solution. We don't yet know how to deal with that, but most of the time, it's either an exponential or some combination of exponential and trig because of Euler's identity. Okay? So we get our solution set. So the procedure is just do the obvious here, solve the homogeneous equation, you get your solution set. Then you figure out a solution to your non-homogeneous equation, which is usually impossible, but the problems I'm going to give you, it's possible. If I put an arctangent over here or something like that, you're not going to solve it. Nobody's going to solve it. Okay? We don't know how to solve it. There's no way to write a closed form function for most of the functions, a closed form solution for most of the applied force functions, but the ones that are really important, the trig functions and the polynomial functions, okay? Power functions, yeah, you can do it, okay? Okay, so our general solution then is x of t equal C1 times 1 plus C2 e to the negative gamma over m t plus f applied over gamma plus d. And this gamma over m is not as clear as I'd like it, but that smudge will help. Okay? Still looks like an R. Let's make sure there's a loop here. There we go. Okay? So the procedure, you should be familiar with it because I've signed it and you've done it. But I wanted to be very specific about it and very clear about it because we want to use this as an example of what we then do with the solution. Now, loop, hard to write a loop, something as blunt as this chalk, but that's gamma, not R. Still kind of looks like an R. That looks like a fancy R. It's a gamma. There, I got a loop. Okay? Why didn't I write D? Well, C1's constant. You don't know what it is. It could be anything.
So it's
D's constant. You don't know what it is. It could be anything. So when you add them, you still don't know what it is. It could be anything. In other words, your constants absorb one another. Okay? So there's your general solution. Now what do we do with this? Okay? Let's suppose gamma equals 3, m equals 12, and x of 0 equals 0, but x prime of 0 equals 4. I'm not putting units with this right now, but I will maybe shortly, maybe just a little later, okay? To make sense of it, I think I'm going to do it shortly, but let's see how you do with this. Okay, so we've got this, this, and this, right? Now, this and this plugged into this allow you to evaluate C1 and C2. Okay? So we want to plug the x of t function in to these equations to get simultaneous equations for C1 and C2, and we solve it. Now I'll just mention that this corresponds to starting in the plane at the point 0, 0 with a slope of 4.